And I again kindly ask everyone to switch off their microphones during the talk. Maxim, you are welcome.
Okay, thank you very much for invitation to make a talk at your seminar. So please do not be very confused with the title, because this talk was prepared precisely for the conference which I participated a few days ago, and just due to some problems with text file in my computer, I was unable to update this file. So please just take into account the title at the top of this slide. So I will speak about some very interesting, in my opinion, phenomena, which in some sense is known about more than 30 years, but advantage which I would like to present at your seminar, and I would like to attract your attention to some phenomena which are not so widely known. So I will speak about local Lagrangian representation. So one of my main interests in this direction is following. We can have local or non-local Hamiltonian structures. The question is it possible for both cases, in some cases, to construct corresponding local Lagrangian representations? So I will speak about one such an example. I would like to shortly describe the technology and explain this phenomena in next slides. So please, this slide. So here I call it first Nutku-Olvers puzzle. I will explain what it means. So at the top of this slide, you can see ideal gas dynamical system. Ideal means that this is ordinary compressible fluid, but nevertheless here no forgot. So here only function u, which is velocity, and only function rho, which is density, and so no isentropy, no any extra field variables. So only these two-component system of equations, well known as a particular example of quasi-linear system of equations in 2 dimensions, x and t. So the fact which is presented at the top of this slide is local Hamiltonian structure of Dubrovin-Novikov type, which was described, at the best of my knowledge, by maybe Novikov in his original paper devoted to multi-dimensional case, and of course it was independently investigated by Yavuz Nutku, and then he continued this investigation in collaboration with Peter Olver. So we have this two-component system. This system has local Hamiltonian structure of Dubrovin-Novikov type. You can see the structure written in canonical variables rho and u, and here you can see at the bottom of this slide corresponding functionals of energy, momentum, and density functional for density rho. So I forgot why I omitted here.
I'm sorry. Do you mean that it is free Hamiltonian, or so
what means free Hamiltonian?
Free Hamiltonian.
No. He is written only one.
Only one. And what? And why H2 and H3? Just to conserve densities? What are they?
I started to say that I don't remember why I forgot to also add here functional H1. H1, this is nothing but integral u dx. So H4 has interpretation is the energy, H3 is a momentum, H2 and H1 are just corresponding annihilators of these Poisson brackets. So here only one.
They are conservation laws.
Yes.
Okay.
Densities of corresponding conservation laws. Yes. So in the next slide, we again consider this system, and Yavuz Nutku and Peter Olver found, as you can see, new local Hamiltonian structure, but not of Dubrovin-Novikov type. So please look again on the previous slide. We have Hamiltonian operator, which is a first order. Actually, in coordinates rho and u, this is constant operator multiplied on operator dx only. But in next slide, you see Hamiltonian operator of third order. So B operator is proportional to R square, where R is a pure differential operator, which they observed as a recursion operator. And in their paper, they referred on results made by Mikhail Sheftel and Vladimir Tishukov, where this technology was applied in two and multi-component cases. So just what is very important, in my opinion, to make some small remarks. So please look at the definition of matrix W. So consequence of operations is following. We take matrix W, then we take its first derivative, and only after that we take its inverse expression. So not opposite way. So we do not take inverse matrix of W and then we differentiate with respect to X. No, first we differentiate W with respect to X, and only after that we take its inverse matrix. So this is, it looks like very sophisticated and maybe just very artificial procedure, but in fact it works. So they introduced this matrix W and they constructed this recursion operator R, and taking into account this expression, they were able to prove that operator B is a Hamiltonian operator of third order, very, very unusual in comparison with Hamiltonian operator previously found by Dubrovin and Novikov.
Max, but I do not understand why. So let's again, we have this W. It is a matrix with functional entries, yes?
Yes.
Then we differentiate it and take inverse. Then
Yes.
we take its derivative, yes? It's again a functional matrix.
Yeah.
Then what we do, we apply this functional matrix to a first order differential operator, and we again
maybe it is smart to use here brackets. It will be more clear if you use brackets.
Which brackets? Well, let me finish. So we apply a zero order operator to a first order operator, and we obtain a first order operator. Why third order? Coefficients are maybe of third order, but operators of first order.
Okay, can I continue?
No, first answer my question.
Yes, can I continue, give answer on your question?
Yes, of course.
So we take matrix W, we take its derivative with respect to X. This is just matrix. Then we take its inverse operator, inverse matrix. This is still a matrix. Then we write recursion operator as dx, and this is composition dx. And
this is a composition. So this is a composition of zero order and first order. Yes, now I understand. Okay. Okay, thank you.
So indeed, it's correct. So we take you see definition of third order pure differential operator B. In right hand side we have Hamiltonian operator of Dubrovin-Novikov, and we apply for this recursion for this Hamiltonian operator twice. We apply twice recursion operator R. This is construction of third order differential operator, which is still local. So we can continue this application as many times as you like. And in all these cases, we will be able to construct local operators of fifth, seventh, and etc. higher orders. This is observation made by Ivo Snutko and Peter Olver. Okay, next slide. So we can formulate plenty questions. I just formulated some of them which were interesting for me. So we would like to explain the origin of this local Hamiltonian structure, because it was just like some unknown phenomena. It was found, but how to explain it? Second question, how to generalize this structure to n component case. The point is that Ivo Snutko and Peter Olver, they were able to find this local third order Hamiltonian operator only for gas dynamics. But my question is it possible to extend this picture for any number of components? Next question is how to recognize that given system can be equipped by such local Hamiltonian structure. Indeed, in many cases, if we have some even quasi-linear system of equations of first order, the question is how to construct, if such a structure exists, how to construct such a Hamiltonian structure is very open question, because at the beginning we should, for instance, formulate what means Hamiltonian structure. I mean, we should have some assumptions which is an ansatz which we are looking for such a Hamiltonian structure. If we are looking for ansatz of first order, this means it will be Hamiltonian structure of Dubrovin-Novikov type that was found by, as I mentioned, just Peter Olden and Yevus Nutku. If we are looking for Hamiltonian structures in different ansatzes, we need to do some machinery and we need to do what to do if we are looking for corresponding Hamiltonian structure in a priori given ansatz. So this is very interesting problem. So I just would like to say that all that I'm talking about in my presentation, I am speaking just about two ansatzes. I don't like to say that these ansatzes can exhaust all possible ansatzes. I don't know. So this is very interesting and open question. Maybe maybe very ambitious. If we have some Hamiltonian system, quasi-linear system, let's look here at the top of this slide. We have quasi-linear system. The question, how many local Hamiltonian structures, even local, this system can admit? And in my opinion, we know at this moment answer. We know infinitely many such local Hamiltonian structures, but nevertheless, because we know ansatzes, but maybe some other people will be able to suggest some other ansatzes, and maybe in such other ansatzes, this system also can be equipped by any other local Hamiltonian structure. So I don't know how to answer on this very general question. Okay, so if we are able to recognize, I am speaking about item 3. Here is item 4, how to construct such a local Hamiltonian structure. Then how many such local Hamiltonian structure can be equipped for given hydrodynamic type system, and also I shall speak about this a little bit later. And finally, the last question is it any relationship between the examples which were presented in previous slides? So we have Hamiltonian structure of Dubrovin-Novikov type, we have Hamiltonian structure found by Nutku-Olver, and the question, is it any relationship between these Hamiltonian structures? So on all these questions, I try to give answers in my talk. So before I will continue, please look on this Lagrangian density. This Lagrangian density was found by me and Yevus Nutku in our common paper about so-called multi-Lagrangian systems. So if you look on this Lagrangian density, which what is very, in my opinion, non-trivial in comparison with all that was known before in theory of such quasi-linear systems of first order. Very, in my opinion, unusual feature is that this Lagrangian density has denominator, where in denominator you see first derivatives with respect to x. I'm speaking about field variables u and rho. And second point is that this Lagrangian density contains field variables u and rho, but not their potential variables. If you look on very well-known models like nonlinear Schrödinger equation, Korteweg-de Vries equation, well-known systems in integrable equations. In all these cases, if you would like to construct corresponding Lagrangian density, you must introduce appropriate potential variables. Here we have direct application of these field variables. So this Lagrangian density is written in these field variables, and moreover, this means that under appropriate point transformations, we can rewrite these Lagrangian densities from, for instance, in this particular case, from field variables rho and u. For instance, you can rewrite to Riemann invariants, because corresponding quasi-linear system can be written also in Riemann invariants. This is a well-known fact for all two-component quasi-linear systems of first order. So this is very, in my opinion, interesting observation, which was made more than 20 years ago by me and Yavuz Nutku, and we just constructed this Lagrangian density. So again, here function f of rho is an arbitrary. Just please let's go back one slide before. So at the top of this slide, you see this function f of rho. So since this function f of rho is arbitrary, this means that we have such an ideal gas dynamical system, which is equipped only by one local Hamiltonian structure of Dubrovin-Novikov type, and by this third order Hamiltonian structure of Nutku-Olver, and corresponding Lagrangian density is unique. I mean unique for any given function f of rho. But later I will give some comments about other possible cases where we can construct corresponding local Hamiltonian structures for different values of f, I mean simultaneously. So I mean, if we take some function f of rho, is it possible for given function f of rho, not for arbitrary, for given function f of rho, is it possible to construct 2, 3, 4, any more number of local Lagrangian representations, which you can see at the bottom of this slide?
Just one question for curiosity. You will speak shortly about Riemann invariance, Maxim.
Yes, yes,
Thank
yes,
you.
Yes.
May I also have a short question or two short questions?
Yes, please.
So please, previous slide about the Hamiltonian structure found by Nutku and Olver. Was the technique of moving frames of Olver included in this search for a new local Hamiltonian structure, or is it unrelated?
Thank you very much for your question. So actually, to be honest, I believe that this structure should be foundable by many different approaches. All that I know, I'm speaking about this paper written by Yavuz Nutku and Peter Olver. It was written, at the best of my knowledge, in 1987. Their statement was following. They utilized recursion operator found at the bottom of this slide, found by Mikhail Sheftel from St. Petersburg and by Vladimir Tishukov from Novosibirsk. So just difference is that, as the best of my knowledge, Mikhail Sheftel found the recursion operator only for 2-component systems of hydrodynamic type, and Tishukov generalized this picture for n-component case. So Yavuz Nutku and Peter Olver utilized these recursion operators found actually in different coordinates systems. I mean, at the best of my knowledge, Tishukov worked in Riemann invariants while Mikhail Sheftel worked in arbitrary coordinates. But nevertheless, they used, I mean, Nutku and Olver, they used knowledge of recursion operator found by these Sheftel and Tishukov authors.
Well, Max, we have Mikhail here, so we can ask him.
Of course, of course.
Well, Mikhail, can you comment Max words? Professor Sheftel.
So, if you're asking me,
yes, well,
I must say that for 30 years I didn't continue research in this field. I changed my field. So now I'm just listening to Maxim's talk, and I have no immediate comments. You know, I just don't remember.
okay, exactly. Thanks a lot. Maxim,
okay, so I start again from this Lagrangian density.
Yeah, maybe, sorry, but related question. Will you comment on how do you find this Lagrangian density, or can you say some small details at least?
if to be honest, I think so that this is not very complicated task, because if you just have some Hamiltonian operator, in some cases you can try to find such operator which is inverse to Hamiltonian operator. This means you should be able to construct symplectic operator. And the question is it possible if such Lagrangian density, yes, Lagrangian representation exists, is it possible in such a case to derive Euler Lagrange equation and interpret this Euler Lagrange equation as an action of appropriate symplectic operator? So from such point of view, this is not so complicated. It was derivation. I believe that if you have just some small experience, you can easily repeat these computations.
Thank you.
If it sounds a little bit artificial, below I try to explain that this is really not so complicated. So let's see. So indeed, let's consider very general ansatz for Lagrangian density. What is a crucial point here is that this Lagrangian density belongs to so well-known class of linearly degenerate densities. What it means degenerate? Because this Lagrangian density is a linear with respect to first derivatives of functions r, k with respect to t. So we have field variables rk, and these rkt derivatives, they're involved in this density only linearly. This means usually such Lagrangian densities people call degenerate, and usually many authors, maybe starting from Paul Dirac, they apply some technology of constraints of so-called first and second kind, but I will avoid this application procedure. I follow maybe to Oleg Mokhov, maybe who was first who utilized this approach. So idea is following. We have Lagrangian density. We should derive corresponding Euler Lagrange equations, and they are just written in this form as M capital. You see at the middle of this slide, and this operator M is just written in very, in my opinion, compact form at the bottom of this slide. So we say that if such Euler Lagrange equations written in this form at the middle of this slide, then we can assume that in some cases we can invert this operator M capital and construct corresponding operator K, which we call Hamiltonian. So we call M operator is symplectic and its inverse operator K is Hamiltonian. So usually in all such similar cases, we have following question. We were able to derive the operator M capital just from definition of given Lagrangian. And once we were able to find this operator M, symplectic operator, the question is it possible to find inverse operator K? You can, of course, ask me what means definition of invertibility. So since I am not an expert in such questions, I could not give you very rigid, very strong definition in such cases. What means inverse operator? My opinion is following. In this case, I call inverse operator K. I mean, Hamiltonian operator K is inverse operator if this operator K contains finite number of operations. So this operator I prefer to have local, or if it's impossible, in such a case, I'm interested to write this operator K in most compact form where all number of operations which I need for construction of this operator K is finite. So I'm sorry if I was unable to clearly explain. So in such cases, I hope to explain my steps in other slides following this one. So now I restrict my consideration on functions gk. You see this first line, gk only on two entries, functions r and its first derivative. So when you see only two entries, I'm speaking about functions gk. This means that index k run the same number as number of field variables r1, r2 up to rn, and all entries r and rx of functions gk, this means 2n entries. So GK depends on R1 up to Rn and R1x up to Rnx. So corresponding earlier Lagrange equations are written below. You see corresponding symplectic operator M. And then if we choose GK not arbitrary, but in form as this set of ratios, HK bar square, in denominator double RKX, in this case, corresponding elements of symplectic operator MII diagonal elements and off diagonal elements MIK, such that you can see in this slide, they have following interesting consequence. Consequence is that if I choose GK in the form which you saw at the bottom of this slide, in this particular case, I was able to construct inverse operator K. That is the point. So again, let me finally say what I would like to tell you on this slide. So at the middle of the slide, you see general expression of symplectic operator where GK depends only on R and its first derivatives. The question is, for me, is it possible to invert this operator M? Actually, if to be honest, I don't know answer on this question. I don't know, is it possible or not to do this procedure? But my claim is more simple. If I choose GK as ratios presented at the bottom of the slide, in such a case, indeed, I was able to invert this operator. So for given symplectic operator, I was able to find corresponding components of Hamiltonian operator K, which you saw in general form as unknown entries at the previous slide. So let me continue. Theorem. This Hamiltonian operator K, as I promised you, has finite number of operations. Here epsilon bar is a constant matrix, constant symmetric and non-degenerate matrix. Then you have some products. W here, Iosif, here again is a number of compositions. W, Rix, dx minus 1.
You mean, before and after dx minus 1, yes?
Yes, so dx minus 1 is acting on everything to the right.
Yes, okay, now I understand, yes.
Yes, so the statement is that this Hamiltonian operator K capital is inverse operator to the symplectic operator, which you just saw in previous slide. And for such a possibility, we need to formulate some statements, which I am going to explain you step by step. So first point is rotation coefficient should satisfy some system of restrictions for two indices I and K. I will a little bit later explain the meaning of these equations. Then we need to introduce some affinors Wi with index alpha, which determine, you see at the bottom of this slide, set of commuting hydrodynamic type systems, which I call them, like many people do in such similar situations, as structural flows, or if you don't like, I can call them basic flows. So in such a case, you see here is a definition of expressions hi bar, h bar with indices alpha and I. And I step by step will explain all these functions, how they can be extracted, how they appear in this picture. So here you remember epsilon constant non-degenerate symmetric matrix appears in this context such that in left-hand side you see this is a set of constants. In right-hand side you see is a sum of products but not constant expressions. This is just the end of theorem. So let me try to explain.
Max, I'm sorry. Again, well, to understand. So this theorem states that under these three conditions, you can take the inverse in your sense,
Yes.
and the result will be Hamiltonian, yes?
Yes, precisely. So at this slide, at the bottom, you see components, diagonal and off-diagonal components of symplectic operator M. Claim is that, so according to these introduced functions hi bar, beta ik, I will explain, of course, all that is written here. So according to this notation, if these rotation coefficients beta ik satisfy this set of conditions and corresponding values hi bar bar with index alpha, then indeed this operator k hat is Hamiltonian. Yes. So let's continue, and I will explain origin of all these objects involved in this construction. So sorry, we have a hydrodynamic type system written at the middle of this slide. Ri tau is ratio hi bar multiplied rix. Here no any summation. So please don't think about this. Here no any summation. And point is that usually in similar situations, we have hydrodynamic type system. Let's go back again to first or second slide. So we have ideal gas dynamical system. This dynamical system written in its physical variables, rho and u. Let me just remind you that u is the velocity of gas, rho is the density. But we know that in two component case, if corresponding characteristic velocities are distinct, such a system every time can be rewritten in diagonal form. So we can find such Riemann invariance Ri that this ideal gas dynamical system can be written in its diagonal coordinates, so-called Riemann invariance. So we can do it every time in two component case. This is not a problem. I mean, not a problem from the existence point of view. So we can do it. Okay, assume that we are able to do it. Point is what to do on next steps. First step is following. We take this system at the middle of this slide in diagonal coordinates. Then we should compute rotation coefficients, beta ik. So this technology was suggested, I don't know who was first who do it. I guess that it was Gaston Darboux. He did it maybe more than 140 years ago, maybe 150 years ago. So these rotation coefficients were used him for construction of corresponding curvilinear coordinate nets, conjugate curvilinear coordinate nets. But we are speaking about not about general theory. We are not speaking about any conjugate curvilinear coordinate nets. We are speaking about some particular cases of curvilinear coordinate nets. And here, before I will continue, I just would like to shortly explain what I'm talking about. So if you look on previous slide, please see on item 1, here is written di beta ki plus dk beta ik. This is important. And here is a sum beta im, beta km. What is important for me here? So if you as people usually do, take any coordinate system. I'm speaking about, again, conjugate curvilinear coordinate net. You can ask, what means flatness condition? Flatness condition is following. If you look on item I, just please look, I will pronounce it. It sounds in following way. di beta ik plus dk beta ki plus sum beta mi beta mk. So if you compare all that I just pronounced now and formula which you saw at the middle of this slide, you see that I used now so-called transposed matrix beta. So if we deal with matrix beta, such a restriction means flatness condition. Here you see I wrote anti-flatness condition. So the same condition where indices were changed according to transposed matrix beta. So if beta rotation coefficients satisfy this anti-flatness condition, this means that we are dealing with not conjugate curvilinear coordinate nets, but with conjugate curvilinear coordinate nets equipped by this anti-flatness condition. So we are not speaking about general theory. This is just a restriction where we should expect existence of such local symplectic operator and such non-local Hamiltonian operator, which you saw at the top of this slide. So next point is that this is just like game we are play in Lego. We have some elements and we would like to construct this corresponding Hamiltonian operator. We need to construct constant matrix epsilon bar. We need to construct this affinors WI with index alpha. And if we were able to do it, this means that we can construct corresponding Hamiltonian operator. So you see, if we have some given rotation coefficients beta ik, which satisfy this anti-flatness condition written in the middle of the slide, we should to solve linear system of equations with variable coefficients written at the bottom of this slide. If we were able to find this H bar with index alpha, this means we were able to reconstruct corresponding affinors WI alpha, and this means that we were able for such hydrodynamic type systems, we were able to construct corresponding Hamiltonian operators. So once you asked me about how these Lagrangian representations can be written, is it difficult or not to find these Lagrangian representations? I just would like to attract your attention again to 2 slides before. So you see, here is a Lagrangian density, which was found again by me and Yevus Nutku, but looks very complicated. Quadratic expression in denominator with respect to first derivatives, linear expression with respect to derivatives with respect to x and with respect to time variables. So once you look on this Lagrangian density, you can ask, it's unclear how such Lagrangian density can be extended to 3-component case, 4-component case, any higher component case. But if you just rewrite this Lagrangian density in Riemann invariants, this expression will be significantly simplified. Significantly means, you please just look here. Corollary, the Lagrangian density is proportional to RK tau over RKX. So every time when we deal with any Hamiltonian, with any hydrodynamic type system which can be equipped by this Lagrangian density, we need to keep in account only that this Lagrangian density has 2 blocks. Hamiltonian density H small of R, and first block which contains in fact hidden symplectic structure. So we have here very simple, in my opinion, technology. Here sum of blocks where HK bar square multiplied on ratio RK tau over RKX. That's all. So this is very simple structure of such Lagrangian density. So just very important feature of this construction. Once you look on this Lagrangian density, assume that you wrote here arbitrary function H. You wrote here arbitrary functions HK bar. And you would like to ask you yourself, is it possible to derive corresponding symplectic operator? Of course, it's easy. We already explained it. However, if you would like to invert this operator, I mean, you would like to, using this symplectic operator, reconstruct corresponding Hamiltonian operator K, of course, this is impossible in general case. Impossible because you need to take into account all information presented in this slide. You need to be able to prove that HK bar here are not arbitrary functions. There are some special set of solutions of appropriate linear system at the bottom of this slide. And only in this case where corresponding rotation coefficients beta ik satisfy anti-flatness condition, only in this particular case, indeed you were able, starting from this Lagrangian density, reconstruct corresponding compact but non-local Hamiltonian operator K. Okay? So here I will speak about local Hamiltonian structures because this observation made by me and Yevus Nutku was also very unexpected. Point is following. Assume bi-Hamiltonian system. First Poisson bracket is just Dubrovin-Novikov structure. Expression for this Poisson bracket is written here, Rij with index 1. Second Hamiltonian structure is non-local. Corresponding components of local symplectic structure are written at the bottom of this slide. So you can compare components of operator A hat for operator M hat. They look very similar, but different. A operator contains Hi bar in denominators. M hat contains H in numerator. First operator.
And deltas have different meaning here. Yes, one delta is Kronecker symbol, and the second delta
yes,
is
of course. Yes, precisely.
function. Yeah, okay.
Yes, if delta contains two indices, this means Kronecker delta. Yes. Thank you. So again, you can just look on operators A hat and M hat. They look very similar, but their origin different and their, how to say, they act in different way. Nevertheless, we again have one local Hamiltonian operator and one local symplectic operator. If we have these two operators, we can of course construct corresponding recursion operator A and M. And I remember my discussions with Raffaele Vitola. I remember also my discussions with Joseph. Question was, is it difficult or not in such cases to prove that these products, I mean A hat, M hat, and their consequences, I mean multiple applications of this recursion operator, is it difficult or not to prove their consistency? Because usually some system has two local Hamiltonian structures, it's actually takes time. Not so easy to prove that this Hamiltonian pair is compatible. But here we have different picture. We have local, not Hamiltonian structures, not symplectic structures, but one local Hamiltonian, but one local symplectic. This is the point. So it looks like, as I understood, explanations given by Raffaele Vitola and Joseph Krasilchik. So in both cases, I mean Hamiltonian and symplectic operators in these cases, in this case, these structures not so complicated to prove that they are compatible. So we have by this, just by this construction, infinitely many local odd order Hamiltonian and symplectic structures, infinitely many. This is very unexpected. It was a very unexpected phenomenon. And I just was very, it looks like curious why it could be such a situation, but actually it works. In many, many such cases, such situation appears, and a little bit later I will speak about it. So let's consider the following picture. We have well-known system for rotation coefficients beta ij, I mean a system of equations for three distinct indices I, j, k. This so-called system of equations for rotation coefficients beta I, j, k, which describes curvilinear coordinate nets. But up to this knowledge, we are dealing with just a general picture. If we add, please see in the left-hand side, di, beta, ik, etc. This is so-called flatness condition. And if you look on right-hand side, di, beta, ki, transposed matrix, this is so-called anti-flatness condition. So all together, these three conditions for three distinct indices and for two distinct indices all together, they can be considered as an integrable system describing such infinite sequence of compatible systems. So if such set of conditions I'm speaking about top of this slide is fulfilled for any given set of rotation coefficients, in this case we can say that corresponding hydrodynamic type system has infinitely many local Hamiltonian structures of all odd orders, and the same statement for corresponding symplectic operators, so we can construct infinitely many of them. All that you can see below is nothing but corresponding so-called Lax representation. If you check consistency of these equations, linear equations for functions h capital with variable coefficients beta, its consistency condition give us coefficients, conditions for rotation coefficients beta at the top of this slide. Example, you can see here at the middle of this slide. So we have hydrodynamic type system with minus some Riemann invariants minus 2 Ri. This is characteristic velocities. In such a case, this hydrodynamic type system has n+1 local Lagrangian representation of the form which you already saw many times in previous slides of my talk. So this is this example is such an example which contains maximum of anti-flat non-local Hamiltonian structures. So you can ask me, of course, why here is such a statement that here is a maximum, but explanation actually is very simple from the following point of view. Many years ago, by me and Zheny Ferapontov, we proved that the hydrodynamic type system with sign, I'm speaking about characteristic velocities, plus some Rm plus R2 plus 2 Ri, such a system has maximum of local Hamiltonian structures of Dubrovin-Novikov type. In these cases, I'm speaking about plus and minus. In both cases, we have rotation coefficients which are transposed with respect to each other. So if we compute rotation coefficients for minus, if we compute rotation coefficients for plus, in both cases, these rotation coefficients are the same up to transposition of these indices I and k. So from such point of view, if hydrodynamic type system with sign plus has n+1 local Hamiltonian structures, this means if we change sign from plus to minus, this means that corresponding number of anti-flatness conditions should be the same. Indeed, it's true, just changing indices in corresponding set of transposed equations. Finally, here is a list. In conclusion, I just give a list of interesting questions which I described in my talk. You can see them. Maybe for me not so important to repeat them, and maybe I will just by this reason concentrate on a statement item which is pre-last. The existence of one local Hamiltonian structure for the Egorov hydrodynamic type system implies the existence of infinitely many local Hamiltonian structures of all odd high degrees. What means Egorov? I just would like to remind, because all of you should know, I guess, many examples in your experience where such a phenomenon you met at least once. Just please look here at the beginning of my slide. This system has a first conservation law. Rho t is a derivative with respect to x of product rho and u. So you should not trust me. You can easily check that that flux rho u is simultaneously a density. So if you take product rho u, you can just compute its derivative with respect to t. And actually, this is written here at the bottom of the slide. I wrote H3 is a functional of a density rho u. So rho u is not only a flux of first conservation law density, but simultaneously, this is a density of another conservation law determined by functional H3. This means this system is of Egorov type. So again, we call hydrodynamic type system as of Egorov type if such a system has two conservation laws where density of the where flux of the first conservation law simultaneously is a density of the second one. So H3 shows us that rho u is simultaneously a flux of first conservation law density or conservation law, and simultaneously as a density of another conservation law. So if such a system has a local Hamiltonian structure of Dubrovin-Novikov type, you see it, this presented in this slide. This means by construction that this flatness condition due to symmetricity of rotation coefficients in this particular case, this consequence of such a procedure, if our system is Egorov, this means that rotation coefficients are symmetric. So in this case, flatness condition simultaneously, immediately becomes anti-flatness. If our system is anti-flatness, if anti-flatness condition is fulfilled, this means that our system has simultaneously non-local Hamiltonian structure found by Nutku-Olver in this case, and we can again construct a recursion operator, apply infinitely many times, and by replication of this recursion operator, we can construct infinitely many of odd orders Hamiltonian structures, local Hamiltonian structures, and local symplectic structures the same. Thank you very much for your attention. I finished here. Thank you.
Thank you, Maxim. Questions, remarks?
Yes, I have a question.
Yes, please.
Maxim, what about the homogeneity of higher order Hamiltonian structures?
You see, it depends what means homogeneity, because let's just look on next slide. So we have W capital. U, rho, f of rho are not homogeneous functions. But if we will speak about homogeneous differential polynomials, of course, this differential expression will be homogeneous. So from such point of view, every time we will keep appropriate number of derivatives. So from this point of view, of course, all higher Hamiltonian operators will be homogeneous, all. Just please remember that every time you will keep in denominator first derivatives of higher and higher and higher orders. Don't forget about this.
Okay, Rafa, you said
Okay, thanks.
more questions, more remarks? Well, then that's it, Max. Thanks a lot.
Thank you.
As always, we meet next Wednesday, and I want to tell you that the session will take place in well, how to say? Well, it will be real. It will be in Moscow Independent University, room 303, the same time, and everyone who wants and who is able is invited to visit us.
Вы правду говорите? То есть мы уже реально будем там, да?
Yes, Oleg, I'm telling truth. I always tell truth. So everyone is invited. Well, at least those who are in Moscow. Well, and better be sure that you have antibodies in your blood.
Joseph, вы будете онлайн все равно, да?
Yes. In any case, yes, the talk will be broadcasted by Zoom. So for remote participants, it will be accessible, and it will be. I hope. Well, we shall make some experiments, but I hope that it will work. And